What does it take to break a promise written in the stars? In the desolate spring of 2020, as humanity held its breath, the cosmos seemed to offer a magnificent distraction, a celestial appointment for a world in desperate need of wonder. It arrived with a name like a titan from mythology, Comet Atlas. Discovered only months earlier, this visitor from the solar system's deepest freeze was behaving in a way that electrified the astronomical community. It wasn't just brightening, it was erupting with a ferocity that defied all conventional models. Week by week, its luminosity surged, doubling, then quadrupling on a schedule that seemed impossibly accelerated. Projections scrawled on whiteboards and programmed into supercomputers across the globe began to paint a breathtaking picture. By the time it was due to swing around the sun in late May, Atlas wasn't just expected to be a faint smudge visible through a telescope. It was on a trajectory to become a generational spectacle, a rival to the great comets of history, perhaps even bright enough to pierce the twilight sky. Its tail, a luminous gash across the heavens, visible to the naked eye for billions of people. It was to be the great comet of 2020, a shared global experience delivered from the void. You see, a comet like this is more than a dirty snowball. It is a ghost from the dawn of time. Atlas began its journey from the Oort cloud, that vast spherical shell of frozen relics encircling our solar system, a cosmic attic where the leftover building materials of planets have drifted in silent darkness for 4.5 billion years. Its epic multi-million-year orbit was finally bringing it back towards the light and warmth of its parent star. As it crossed the orbit of Jupiter, the sun's faint heat began to work its alchemy. Ancient ices untouched since before the Earth had oceans started to sublimate, turning directly from solid to gas. This process, a gentle outgassing in the vacuum of space, creates the coma, the beautiful ethereal atmosphere surrounding the cometary nucleus and the magnificent tail that follows. The more volatile the ice is, the more dramatic the show. And Atlas, it seemed, was spectacularly volatile. It was a cosmic firework with a long, slow-burning fuse that was now rapidly approaching the flame. The world watched, waiting for the explosion of light. We were promised a marvel, a sign of cosmic grandeur in a time of terrestrial confinement. The universe, it appeared, had not forgotten us. But the universe keeps its own counsel, and its promises are often riddles wrapped in light and gravity. In late March, the first whispers of doubt began to circulate. The relentless brightening, the defining characteristic that made Atlas so special, suddenly faltered. It was like a powerful engine sputtering without warning. Seasoned observers, both amateur and professional, stared at their new images with a growing sense of unease. The numbers coming back from their photometers were no longer climbing, they had plateaued. Then they began to drop. A collective, confused silence fell over the community. This was not in the script. Comets can be fickle, certainly, but for a large inbound object to simply run out of steam, so far from the sun, was deeply strange. It was as if a marathon runner leading the race and showing no signs of fatigue had simply decided to stop running miles before the finish line. The models were thrown into disarray. Was it coated in an unusually thin layer of volatile ice that had now boiled away, leaving a dark, inert core? Was it undergoing a temporary structural change? The explanations were tentative, unsatisfying. They failed to capture the sheer strangeness of the event. The comet wasn't just fading. Its very heart, the central condensation of light that marked its nucleus, was beginning to look unwell. It was becoming soft, elongated, indistinct. The celestial celebrity was suddenly looking ghostly and frail. The mystery deepened into a profound slow-motion catastrophe. On April 11th, a team of astronomers using a remote observatory confirmed the worst fears. A single sharp point of light was gone. In its place was a fuzzy, misshapen streak. Something fundamental had happened. The call went out to the greatest eye we have on the heavens, the Hubble Space Telescope. Pulled from its other duties to act as a cosmic detective, Hubble slewed its gaze towards the fading phantom. What it sent back were not images of a comet, but of a celestial shipwreck. Atlas was dead. It had not merely fizzled out, it had disintegrated. The images were haunting, ethereal, and utterly unprecedented in their clarity. Where there should have been a single solid nucleus a few kilometers across, Hubble revealed a ghostly chain of shattered fragments. Dozens of them, some the size of a house, were drifting apart, each trailing its own pathetic, wispy tail of dust and gas. It was a funeral procession in the dark. The great comet of 2020 had shattered into a cloud of cosmic shrapnel, a spectre of what might have been. The promise of a heavenly spectacle had been broken, replaced by one of the most profound and public cometary disintegrations ever witnessed. The question that echoed through observatories and university halls was immediate and deeply unsettling. Why comets do break apart, but typically they do so under the influence of two powerful forces. They can be ripped asunder by the immense gravitational tides of a close pass by the Sun or a giant planet like Jupiter, a process of being stretched and torn by gravity itself. Or as they near the Sun, the intense heat can cause a cataclysmic eruption of subsurface ices, a thermal shock that blows the fragile nucleus to pieces. But Atlas was a victim of neither. When it began to crumble, it was still more than 160 million kilometers from the Sun, farther away than the Earth, in a region of space far too cold for thermal stresses to be the primary culprit, and it was nowhere near a massive planet. It was dying alone in the quiet, cold emptiness of the inner solar system, seemingly of its own accord. It was as if a mountain had spontaneously crumbled into dust without an earthquake or an eruption. The physics didn't add up. Its death was an anomaly, a failure of our most trusted models of how these ancient wanderers live and die. This profound explanatory gap opened the door to more exotic, more tantalizing possibilities. In the wake of Oumuamua and Borisov, the first confirmed interstellar visitors, a new question began to be whispered. Could Atlas be another one? Could it be a traveler from another star system masquerading as one of our own by virtue of its orbit but built differently? Perhaps interstellar comets formed in the alien chemistry of another star's protoplanetary disk are structurally weaker, more fragile than our own homegrown variety. Its bizarrely rapid brightening could have been the sign of a body so delicately constructed that even the faintest warmth of the distant sun was enough to trigger a runaway disintegration. This idea that we were witnessing the death of an alien comet cast the entire event in a new, more mysterious light. It was a compelling narrative, but it rested on speculation. There was no direct evidence of an exotic origin, only the unexplained strangeness of its demise. The mystery of Comet Atlas became a cosmic cold case, a set of beautiful, haunting images of a death without a clear cause. The celestial ghost story needed a solution grounded not in speculation, but in a deeper, more nuanced understanding of the forces at play. And that is where our story truly begins. Because now a revolutionary new trajectory model is emerging, one that looks back at the final frantic weeks of the comet's life and sees not a simple act of self-destruction, but a far more intricate and violent drama. This new analysis suggests that Comet Atlas was not merely a passive victim of its own fragile nature. Instead, it was an active participant in a cosmic dance with a hidden, brutal partner, the Sun's gravitational field, but in a way we have never fully appreciated. The data points to an almost unbelievable phenomenon, a newly proposed mechanism for cometary destruction known as a gravity break. It is a concept that sounds like science fiction, yet it may be the key to this entire puzzle. It proposes that under very specific orbital conditions, a comet's own momentum and the subtle, relentless torque of solar gravity can conspire to create a catastrophic internal failure. It suggests that the comet's nucleus, spinning like a top as it hurtled through space, was subjected to a twisting force so powerful it created a shear point, a cosmic fault line deep within its icy heart. It wasn't ripped apart by a close pass, nor was it boiled into oblivion. According to this model, Atlas was wound up by its own trajectory until it reached a breaking point, a suicide pact written into the very laws of motion and gravity that governed its path. This idea is radical. It challenges decades of cometary science. It suggests that the solar system is a more mechanically hazardous place than we ever imagined, with invisible gravitational whirlpools capable of dismantling an object from the inside out. But if this gravity break model is correct, it doesn't just solve the mystery of one failed comet. It gives us a powerful new tool, a new lens through which to view the entire life cycle of these celestial nomads. How many other comets that fizzled out unexpectedly were not duds but victims of this same gravitational sabotage? How does this force shape the evolution of the Oort cloud and the delivery of water and organic materials to young planets? The death of Comet Atlas, once a source of deep disappointment, may have inadvertently become the single most important cometary event of the 21st century. It has forced us to ask a new question. We are no longer just asking what Atlas was made of or where it came from. We are now confronting a far more profound inquiry. Did we witness the birth of a new law of cosmic physics, a hidden rule of the road in our solar system revealed to us in the beautiful ghostly wreckage of a comet that failed to keep its promise? Do you remember the final moments of the old world, the quiet exhale of a decade, giving way to the new? In the closing weeks of 2019, as humanity turned its gaze inward toward holidays and resolutions, a machine kept its unblinking eye on the heavens. It wasn't searching for prophecy or spectacle. Its mission, etched into its code, was one of vigilance, a tireless sentinel against cosmic threats. This was Atlas, the Asteroid Terrestrial Impact Last Alert System, a pair of robotic telescopes in Hawaii scanning the sky night after night for anything that moved against the steadfast backdrop of the stars. Its purpose was pragmatic, a shield against the unthinkable. But on the 28th of December, it found something else entirely. It found a promise. It appeared as nothing more than a faint anonymous smudge of photons, a barely there whisper in a torrent of digital data. In the silent automated world of celestial surveys, countless such apparitions flicker into existence and fade away dismissed as sensor noise or distant, uninteresting rocks. This particular ghost, however, refused to vanish. On the next pass, it was there again, having drifted ever so slightly a microscopic crawl across the infinite black. The system flagged it, assigned it a provisional designation, and sent the alert out into the world. To the global community of astronomers, it was just another notification in a ceaseless stream, another puzzle piece to be catalogued. They named it C, 2019Y, for a label as sterile and functional as a lab sample. C for Comet, 2019 for the year of its discovery. Y4 to mark its place in the sequence of finds from the last half of December, a name without poetry for an object not yet understood. But the universe rarely cares for our mundane taxonomies. This faint smudge, this C, 2019Y4, was carrying a secret. As telescopes around the world, both immense professional observatories and humble backyard instruments, swiveled to get a better look, a picture began to emerge. The initial data points were plotted tentative dots on a graph that represented a journey of unimaginable scale. From these first few breadcrumbs, mathematicians and astronomers began to trace its path backwards, to calculate the shape of its orbit, to write the opening lines of its story. And what they found sent a current of electricity through the astronomical world. The object was on a trajectory that would carry it deep into the inner solar system, a path that would bring it breathtakingly close to the Sunday. This proximity to our star is the crucible in which a comet is forged. For millennia, perhaps millions of years, this object had slumbered in the profound, absolute cold of the outer solar system, a pristine snowball of frozen gases, dust and rock from the dawn of creation. It was a time capsule preserving the raw materials from which our worlds were built. Now it was falling inward, answering a gravitational summons that had been issued before human history began. As it drew nearer to the sun, the gentle warmth of that distant star began to stir it from its long sleep. The ice on its surface started to sublimate, transitioning directly from a solid to a gas erupting into the vacuum of space. This process, a kind of celestial shedding, creates the beautiful ethereal envelope of gas and dust we call a coma, the glowing head of the comet. It is this coma that catches the sunlight that makes a comet visible, that transforms a dark, inert rock into a celestial beacon. And C, 2019, Y4 was brightening. It was brightening at a staggering, almost unprecedented rate. The initial observations suggested a small, dim object, perhaps only a few kilometers across. But with each passing week, it grew more luminous, defying all predictions. The curve of its brightening was not a gentle slope. It was a steep, audacious climb. Astronomers use a simple formula to forecast a comet's future brilliance, an equation based on its distance from the Sun and its distance from Earth. For Atlas, the numbers just didn't seem to add up. It was behaving like a much larger, much more active body outgassing with a ferocious intensity that belied its humble origins. Whispers began to circulate on forums and academic mailing lists. Could this be it? Could this be the one we've been waiting for? The dream of a great comet is a recurring one, a deep-seated desire in both the scientific community and the public imagination. These are not your average faint fuzzballs that require a powerful telescope and a star chart to locate. A great comet is an event. It's an apparition so brilliant it can be seen with the naked eye from city skies, a majestic plume of light that can stretch across a significant portion of the celestial sphere. They are celestial performers that upstage the constellations themselves. Comets like Hale-Bopp in 1997, a twin-tailed marvel that graced our skies for a staggering 18 months, or Hyakutake in 1996, with its ghostly blue tail stretching halfway across the heavens. These events are seared into the memory of a generation. They connect us in a primal way to the cosmos and to our ancestors who looked up at these same apparitions with a mixture of terror and awe. And now the data for C 2019 Y4 was hinting that it might join this hallowed pantheon. Projections still early but tantalizing suggested that by the time it reached perihelion, its closest approach to the Sun, in late May 2020, it could rival the planet Venus in brightness, perhaps even becoming visible in broad daylight. The stage was being set for the astronomical show of the decade. The public caught on quickly. News articles began to appear, their headlines glowing with optimistic predictions. Comet Atlas was no longer just C 2019 Y4. It was the great comet of 2020, a celestial gift to a world on the cusp of a difficult year. Amateur astronomers began tracking it obsessively, sharing their images of the small greenish fuzzball growing steadily more impressive with each passing night. It became a shared project, a global source of wonder and anticipation. You could feel the collective gaze of the planet beginning to turn upward. We were all being drawn into its story, becoming spectators in a grand cosmic drama whose script seemed to have been written eons ago. We believed we were about to witness a triumphant journey, a glorious pilgrimage into the heart of our solar system. But beneath this popular narrative of impending spectacle, a deeper, more perplexing mystery was unfolding within the precise, unforgiving world of orbital mechanics. As more observations poured in from around the globe, the comet's trajectory was being refined with ever-increasing accuracy. Every new position, every timestamp, was another pin in the map of its journey, allowing computers to draw its path with more confidence. The crucial number they were all trying to nail down was its orbital eccentricity. This single value, this elegant mathematical descriptor, tells you everything you need to know about the fundamental nature of an object's path through space. An eccentricity of 0 describes a perfect circle, the idealized orbit of a planet in a textbook. An eccentricity between 0 and 1 describes an ellipse, a stretched-out circle, the path followed by every planet, asteroid, and short-period comet in our solar system. These are the bound members of our cosmic family, forever tethered to the Sun's gravity, destined to repeat their journeys over and over again. But what happens when the eccentricity reaches 1? At precisely 1, you have a parabola. This is the perfect escape trajectory. An object on a parabolic path has just enough energy to break free from the Sun's gravitational grip. It will make one pass, one dramatic flyby, and then coast back out into the void, never to return. This is the signature of a long-period comet, a visitor from the Oort cloud, that vast spherical shell of icy bodies believed to surround our solar system at its farthest frontiers. These are the true nomads flung inward by some distant gravitational nudge, making their very first and perhaps only trip to the inner solar system. For all intents and purposes, their journey is a one-way street. Then there is the final frontier, the realm beyond 1. If an object's eccentricity is calculated to be greater than 1, its path is not a parabola but a hyperbola. A hyperbolic trajectory is not just an escape, it is an emphatic high-speed rejection. It means the object is moving too fast, possesses too much kinetic energy to have ever been a member of our solar system. The Sun's gravity can bend its path, pulling it into a wide curve, but it can never capture it. An object on a hyperbolic path is a tourist, a traveller from somewhere else entirely. It is a castaway from another star system, an interstellar interloper, and in the early days of January 2020, the orbital solution for C 2019Y4, refined with the first few weeks of data, returned an eccentricity that was startling. The number was something like 1.0008. For a fleeting, breathtaking moment, the implications of that tiny figure, that minuscule fraction above the threshold of 1, hung in the air. Could it be? Could this brilliant comet, this object that was already promising a historic spectacle, also be an emissary from another sun? The timing was electric. The astronomical community was still buzzing from the recent discoveries of Oumuamua in 2017 and 2I Borisov in 2019. For centuries we had theorized that objects from other star systems must be passing through our own, but we had never seen one. Then in the span of just 2 years we found two. Oumuamua was a bizarre cigar-shaped enigma that tumbled past us before we could get a good look. Borisov was more obliging. It looked and behaved just like one of our own comets, but its hyperbolic trajectory was undeniable proof of its alien origins. These two discoveries had thrown open the doors to the new field of interstellar studies. We were just beginning to learn how to spot these visitors. We had found 1I, the first interstellar object. We had found 2I, and now the initial data for this new comet was screaming that it might be 3I. Unofficially, some began to refer to it as 3I, Atlas. The designation was premature, a product of pure excitement, but it captured the extraordinary possibility that felt for a moment within our grasp. Think of what it would mean. A third interstellar object discovered less than a year after the second. It would suggest that these travelers were far more common than we had ever dared to imagine, that the space between the stars was not an empty void, but a galactic highway teeming with wandering worlds. And this one was different. Unlike the faint and distant Borisov 3I, Atlas was projected to be bright, close, and spectacular. It wouldn't be a subject just for the world's most powerful telescopes. It would be a visitor from another star that you could see with your own eyes, a tangible link to a distant, unknown planetary system painted across our twilight sky. The potential for scientific discovery was immense. By analyzing the light from its outgassing coma, we could determine its chemical composition, providing a direct sample of the building blocks of another solar system. We could compare its makeup to our own comets, searching for similarities that might hint at a universal recipe for planet formation, or for exotic differences that would rewrite our understanding of cosmic chemistry. The debate raged in the quiet corners of the internet where astronomers gather. Was the hyperbolic signal real, or was it an artifact of an incomplete dataset? The argument for it being an error was strong. When you have only a short observational arc, just a few weeks of data for an object on a journey that lasts millennia, small measurement errors can be magnified, leading to wildly inaccurate orbital solutions. It's like trying to predict the final destination of a cross-country train by watching it move for only a few inches. Furthermore, the comet was still very far away, out beyond the orbit of Mars. At such distances, non-gravitational forces can play a significant role. The very act of outgassing that was making the comet so bright also acts like a set of tiny, unpredictable rocket thrusters. This jetting effect, caused by gas erupting from its sun-warmed surface, can gently push the comet off its purely gravitational path, subtly altering its trajectory. Without being able to model these forces, precisely calculating an exact eccentricity was fraught with uncertainty. The tiny value above 1, 0, could easily be noise, a phantom in the calculations that would evaporate with more data. And that is exactly what happened. As January turned to February, the observational arc grew longer. Day by day, week by week, astronomers continued to feed new positions of Comet Atlas into their computer models. The path became clearer, the uncertainties began to shrink, and the truth began to solidify. With each new run of the simulation, the value of the eccentricity edged downward. It fell from 1.0008 to 1.0004, then to 1.0001. It teetered on the very brink of the parabolic line, the knife's edge between being a visitor and a member of the family. Finally, with a month and a half of solid tracking data, it crossed the threshold. The number settled at a value of approximately 0.999, and with more refinement, it locked in. The final verdict was clear. C. 2019Y 4 Atlas was not an interstellar object. It was one of ours. It was a long-period comet, a native of the Oort cloud, just as the vast majority of such objects are. The brief, exhilarating dream of 3I, Atlas, was over. There would be no alien chemistry to study, no tangible link to another star visible to the naked eye. For some, it might have felt like a disappointment, a demotion from something profoundly exotic to something merely spectacular. But in science, every answer, even one that dashes a tantalizing hope, is a victory. The narrative was now settled. We had found a domestic treasure, not a foreign dignitary. We had discovered a pristine relic from the birth of our own solar system, and it was on a pilgrimage to the sun that promised to be one for the ages. Its identity was confirmed. Its trajectory seemed to be set in stone, a predictable gravitational clockwork that we could now model with exquisite precision. We knew where it had come from, and we knew exactly where it was going. We had its story all figured out, but we were about to learn that comets do not always follow the scripts we write for them. Atlas had another secret, far stranger than its imagined interstellar origin, and the forces that would govern the next chapter of its life were not yet visible in any of our equations. The show was just beginning, but the main character was about to go spectacularly off script, and so the celestial pilgrimage began. Having crossed the unfathomable gulf between the stars 3I, Atlas now fell inexorably inward, a captive of the one star that mattered. Its trajectory, a magnificent sweeping hyperbola, was taking it on the ultimate journey for any comet, a close, fiery encounter with our Sunday. In the global community of astronomers, there was a palpable thrum of anticipation, a collective holding of breath that stretched across continents and time zones. This was not just another icy visitor from the distant Oort cloud, the frozen attic of our own solar system. This, we believed, was something far more profound, an emissary from another sun, carrying within its frozen heart the chemical fingerprints of a place we may never reach. The initial calculations painted a spectacular future. As Atlas raced closer, the sun's escalating warmth would work on its ancient ices, transforming it from a dim, faint smudge into a glorious spectacle. The predictions were intoxicating. It was on a path to become the brightest comet in decades, a shimmering beacon potentially visible with the naked eye even in twilight skies, a celestial scimitar of green and white hanging in the firmament for all of humanity to see. For a time, it seemed poised to live up to this stellar billing. Week by week, it brightened its light curve, climbing steadily, perfectly on schedule. Ground-based observatories and amateur skywatchers alike tracked its progress, their data points adding to a growing chorus of excitement. Here was a traveler delivering on its promise, a cosmic event unfolding exactly as the laws of physics dictated it should. We were watching the grand, predictable clockwork of the heavens in motion, a beautiful and reassuring display of orbital mechanics. The comet's path was a known quantity, a line drawn through space by the unwavering force of gravity. Or so we thought. The first sign that something was profoundly wrong was not a bang but a whisper. It was a subtle, almost imperceptible deviation, a tiny ghost in the machine of celestial motion. By late March 2020, the most precise tracking systems on Earth began to register a minute discrepancy. Atlas was not precisely where our models insisted it must be. It was lagging ever so slightly, a microscopic drift from its gravitationally ordained track. Now, for a comet, this isn't entirely unheard of. As they warm up, they don't just glow, they become active. Jets of gas and dust erupt from their surfaces, turning these icy bodies into miniature, unpredictable rocket ships. These non-gravitational forces, the outgassing from solar heating, can gently nudge a comet off its perfect orbital path. Astronomers are well acquainted with this phenomenon and routinely factor it into their calculations. But the deviations seen in Atlas felt different. It was strangely sluggish, less a powerful push from a singular jet, and more a kind of cosmic malaise. The change in its momentum didn't neatly align with the expected behavior of sublimating ices. It was as if the very engine driving the comet was sputtering, losing its coherence. The perfect, predictable clockwork suddenly had a gear that was slipping a tick, that was slightly out of time with the rest of the universe. This subtle anomaly was the first crack in the beautiful story we had been telling ourselves, the first hint that this interstellar messenger was not behaving according to any known script. It was a premonition, a quiet warning that our assumptions were about to be shattered. While the orbital mechanics experts puzzled over this subtle drift, a far more visible and alarming drama began to unfold. The very source of the comet's anticipated glory, its brilliance, began to fail. Comets are supposed to grow brighter as they approach the sun. It is their single most defining characteristic. The physics is simple and undeniable. More heat means more sublimating ice, which means a larger, more reflective coma of gas and dust, which in turn means a brighter object in our telescopes. Atlas, however, decided to defy this fundamental rule. At the very moment its light curve should have been rocketing upwards, it plateaued. Then, to the astonishment of everyone watching, it began to fade. The steady climb in brightness that had fueled so much excitement faltered, then stopped, then reversed. It was like watching a magnificent bonfire promised to roar into an inferno suddenly dwindle to a pile of smouldering embers. Each new observation confirmed the impossible. Atlas was dimming and dimming rapidly. The vibrant greenish coma that enveloped its nucleus appeared to grow more diffuse, less concentrated. The comet was losing its vitality, its radiance bleeding away into the vacuum of space. The hope of a naked-eye spectacle evaporated, replaced by a deepening sense of scientific confusion. What could possibly cause a comet to weaken as it approached its primary source of power? The theories began to fly, each more desperate than the last. Perhaps a thick crust of dust had formed on its surface, insulating the volatile ices beneath from the sun's rays and effectively smothering its activity. Or maybe it had already expended its most volatile, easily vaporized materials during its long journey, leaving it with little fuel left to burn for its grand finale. But none of these explanations felt complete. They were attempts to fit an extraordinary event into an ordinary framework, to explain away a behavior that felt fundamentally alien. The dimming was not just a disappointment, it was a paradox. It violated our foundational understanding of how these cosmic icebergs operate. We were no longer watching a triumphant visitor preparing for its perihelion performance. We were watching a celestial ghost, a fading apparition giving up its light long before its time. The sense of mystery was no longer a subtle undercurrent. It was a roaring tide of bewilderment. The universe was presenting us with a puzzle, and we were beginning to realize we didn't even have the right pieces to solve it. And then, in the first week of April 2020, the mystery transformed into outright shock. The quiet fading, the subtle drift, these were mere prologues to the main event. Amateur astronomer Jose de Quiroz, imaging the comet from his personal observatory, was among the first to notice something catastrophic had occurred. The core of the comet, the single point of light that defined its heart, no longer looked like a single point. It appeared elongated, fuzzy, distorted. His alert sent shockwaves through the professional community. The world's most powerful eyes were immediately turned towards the ailing comet. The call went out to the Hubble Space Telescope, our unparalleled sentinel in orbit, to get a definitive look. On April 20th, Hubble slewed its gaze towards Atlas, and what it saw stopped everyone in their tracks. There was no comet. Not anymore. In its place was a funeral procession. The single solid nucleus of 3I, Atlas, had ceased to exist. Where there was once one object, Hubble saw a string of faint tumbling fragments, a ghostly chain of cosmic debris. High-resolution images taken 3 days later confirmed the devastation. The comet had disintegrated into as many as 30 distinct pieces each, a miniature icy shard of what was once a cohesive whole. Some were the size of a house, others larger, all of them enveloped in a shared, sun-swept shroud of dust and gas. The interstellar traveler had died. It had not been killed by the sun's overwhelming tidal forces, which can rip comets apart when they pass too close. Atlas was still more than 160 million kilometers from the sun, far outside that gravitational kill zone. It had not been vaporized by solar heat. It was still in the relatively cold reaches of the inner solar system. It had simply fallen apart. The crystalline heart of this ancient wanderer had spontaneously shattered, dissolving into a cascade of glittering fragments long before its moment of greatest trial. This was unprecedented. We have seen comets break apart before, but almost always under the extreme duress of a close solar pass, or the immense gravitational pull of a giant planet like Jupiter. For a comet to self-destruct so far out for no apparent reason was a phenomenon that challenged the very bedrock of cometary science. The carefully constructed models of cometary stability, the physics that governs how these bodies hold together, were utterly incapable of explaining what we were seeing. The comet of the century had become the enigma of the century. The aftermath was a storm of scientific debate and frantic theorizing. The global astronomical community, now faced with a cosmic crime scene, scrambled to find a culprit. One leading idea was that the comet had literally spun itself to death. As the ices on its surface sublimated, the resulting jets of gas might not have been uniform. If they were aligned in just the right way, they could have acted like tiny thrusters, slowly spinning the nucleus faster and faster. This celestial pirouette could have increased in velocity over days or weeks until the centrifugal forces overwhelmed the fragile internal tensile strength holding the icy body together. In this scenario, Atlas would have torn itself apart from the inside out, a victim of its own accelerating rotation. It was a plausible, elegant theory, yet it lacked definitive proof. Another camp of thought focused on a more explosive demise. Perhaps the comet's journey towards the sun had heated its interior in a complex and uneven way. This could have caused pockets of super volatile ices like frozen carbon monoxide or nitrogen buried deep within the nucleus to flash boil into gas. The immense pressure from this trapped gas could have built up until it reached a critical point, triggering a catastrophic internal rupture that blew the comet apart like a faulty pressure cooker. This explained the suddenness of the event, but it was difficult to reconcile with the initial gradual dimming. An explosion should have produced a massive temporary surge in brightness from the newly exposed material, not a slow, protracted fade. A third possibility was more subtle, suggesting a kind of structural fatigue. This interstellar visitor, perhaps formed under entirely different conditions in its home system, may simply not have been built to withstand the thermal stresses of our solar system. The repeated cycle of warming and cooling as it rotated day and night on a tiny frozen world could have created microscopic fractures throughout its structure. Over time, these tiny cracks could have propagated and linked together progressively, weakening the entire body until it reached a tipping point of catastrophic failure. It wouldn't have been one single event, but a death by 1,000 cuts, a gradual crumbling that finally led to a total collapse. Each theory had its champions and its critics. The data we had was both breathtaking and maddeningly incomplete. We had watched a comet die in real time, but the cause of death remained elusive, shrouded in a fog of conflicting evidence and conjecture. The beautiful, clean narrative of an interstellar visitor had dissolved along with the comet's nucleus. In its place was a messy, complex, and far more profound mystery. The questions now outnumbered the answers by an order of magnitude. What was Atlas really made of? Was its composition so fundamentally different from our own comets that our models simply didn't apply? Did the conditions of its birth doom it to this spectacular premature end? The object we had hoped to study was gone, replaced by a field of debris. But in that debris, in that scattered trail of cosmic shrapnel, lay the clues. The investigation had only just begun. The ghost of 3I, Atlas, was now leading us down a new, unforeseen trajectory, one that promised to challenge everything we thought we knew about these mysterious travelers from the dark. The equations that had governed the cosmos for centuries were failing us. Newton's elegant mechanics, the very bedrock of celestial prediction, were producing not answers but noise, static, a digital scream of impossibility. For every path plotted for the doomed comet 3I, Atlas the universe offered a defiant contradiction. The models, for all their power, were blind. They were built for a universe of perfect spheres and predictable forces, treating comets as simple solid cannonballs hurled by gravity's hand. But Atlas was no cannonball. It was something wilder, more complex, and infinitely more fragile. The disconnect was a chasm, a gaping wound in our understanding, and into that chasm the greatest minds in planetary science prepared to leap. What followed was not the work of one observatory or one nation, but a quiet, urgent convergence of intellect, a global summons. From the sun-scorched plains of the Atacama Desert to the sterile, clean rooms of supercomputing facilities in Europe and North America, a new kind of expedition was being mounted. This was not an exploration of space with rockets and steel, but an exploration of possibility waged with logic and light. The goal was audacious, almost arrogant in its ambition to build a ghost. They would resurrect 3I, Atlas not in ice and rock, but in pure information, crafting a digital doppelganger so faithful to the original that it would live, breathe, and most importantly die in the same way. This was the genesis of the new trajectory model. It began not with physics, but with data, an avalanche of it. The team built a virtual scaffold, a framework in the machine, and then began pouring in every photon of light, every scrap of information humanity had ever gathered on this enigmatic visitor. The floodgates opened. High-resolution images from Hubble, which had captured the comet's death throes, were fed into the system, not as pictures, but as three-dimensional maps of debris, each pixel a clue to the violence of the breakup. The continuous, unblinking stare of the test satellite provided the comet's heartbeat a light curve, so detailed it revealed not just the object's spin, but the subtle wobble, the growing instability in its rotation. From Earth, the world's great telescopes contributed their own spectral analyses, breaking down the faint light from the comet's coma into its chemical fingerprint, revealing the precise recipe of the ices that were fueling its journey. Methane, carbon dioxide, the signature of water vapor, each one a vital ingredient for the simulation. But even this torrent of information focused on a single object was not enough. The model needed a deeper education, a sense of history. So they fed it the ghosts of other comets, decades of archived observations. The fiery plunge of Shoemaker-Levy 9 into Jupiter, the slow, graceful fizzle of Ison, the startling outburst of Holmes. Each one became a lesson, a memory for the growing artificial mind. The machine learned what it meant to be a comet, to be a loose collection of primordial ice and dust, a fragile time capsule from the birth of everything we know. It was an undertaking of almost unimaginable scale, a digital pyramid built from petabytes of data requiring computational power that could simulate the climate of an entire planet. For months, the world's most advanced supercomputers did nothing else. They were dedicated to this one singular purpose, to resurrect a single shattered piece of ice and force it to reveal the secret of its own demise. The old models had treated gravity as the undisputed king, the only force that truly mattered in the celestial dance. All other factors were dismissed as rounding errors, trivialities. The new trajectory model rejected this dogma entirely. It was built on a revolutionary trinity of forces, a complex interplay of energies that together would write the comet's fate. The first of these forces was the one that gave the comet its beauty and its treachery, the non-gravitational engine roaring from within. As Atlas drew closer to the sun, it was not merely a passive object being heated, it was waking up. The model didn't just approximate this, it simulated it molecule by molecule. Pockets of frozen gases locked away for 4.5 billion years began to sublimate, turning directly from solid ice into vapor. On the screen you could see it. Not a gentle, uniform glow, but a chaotic, violent venting. Plumes of gas erupted from fissures in the nucleus, acting like randomized, unpredictable rocket thrusters. One jet rich in carbon monoxide would fire for several hours, pushing the comet subtly off its gravity-prescribed course. Then, as the comet rotated, that jet would turn away from the sun and fall silent, while another on the opposite side would roar to life. The model calculated the thrust of each of these outbursts, factoring in the composition of the gas and the angle of the plume. It was a celestial ballet of tiny persistent nudges, each one pushing Atlas further from the path of mathematical purity. Alongside this internal engine was an external pressure, a force so delicate it can barely be measured, yet so relentless it can move mountains given enough time and a large enough sail. Solar radiation pressure. The unending stream of photons from the sun, the sheer physical impact of light itself, was striking the vast dusty cloud of the comet's coma. The model treated this coma not as a simple haze, but as a cosmic sail miles wide and exquisitely sensitive. As the comet spewed more dust, the sail grew larger, catching more of this stellar wind and pushing the nucleus ever so slightly. It was a whisper of a force, but it never, ever stopped. The model showed us how these two non-gravitational forces worked in a destructive feedback loop. More heat created more outgassing, which released more dust, which created a bigger sail for the solar wind, which pushed the comet more, exposing new angles of its surface to the sun, creating even more heat. The gentle warmth of the inner solar system had become a celestial blowtorch, and Atlas was caught directly in its flame. This was the first pillar of the new understanding. The comet was not just falling, it was flying, erratically powered by its own self-destruction. The second pillar of the model required the scientists to stop thinking like astronomers and start thinking like geologists. They had to look beyond the external forces and journey deep inside the nucleus itself. For centuries, we had imagined comets as solid, dirty snowballs. The new model erased that simplistic image forever. It rendered 3I Atlas as what it truly was, a rubble pile. A loose agglomeration of countless smaller bodies, ice-glued pebbles, and frozen boulders barely held together by their own feeble gravity. It was not a single coherent object, but a fragile coalition born from the gentle collisions of primordial matter in the cold, dark nursery of the solar system. And like any structure built from rubble, it was riddled with weaknesses. Using data from the breakup of other comets, the model began to populate the virtual nucleus with internal fault lines, invisible fissures, and stress fractures buried deep beneath the surface. It simulated regions of different densities, placing solid rocky inclusions next to pockets of porous, feathery ice. It created a digital anatomy of chaos. This virtual structure was then subjected to the immense differential pull of the Sunday. We call it tidal force. The same force that raises the oceans on Earth was trying to tear Atlas apart. The model showed this in agonizing detail. The side of the nucleus facing the sun was pulled more strongly than the side facing away, creating a constant stretching tension across its entire body. It was like pulling on a block of poorly mortared bricks from opposite ends. For a solid planet, this stress is trivial, but for a loosely bound rubble pile, it was a death sentence. The simulation revealed these tidal forces worming their way into the pre-existing weaknesses. A tiny ancient fracture dormant for eons would begin to widen. A region of loosely packed ice would start to shift and shear against a more solid core. The comet was humming with internal stress, a geological scream that was completely undetectable from the outside. While the external forces were pushing the comet off course, these internal dynamics were priming it for a catastrophic failure. The model showed that the comet's structural integrity was collapsing from the inside out. It was becoming a cosmic egg with an increasingly fragile shell, and the pressures, both internal and external, were building towards a shattering crescendo. This was the second pillar, the understanding that the comet was not just an object, but a place, a landscape of profound weakness whose very construction made its destruction inevitable. The third and final pillar of the model was perhaps the most elegant and the most violent, the dynamics of rotation. The light curve data from TESS had already told us the comet was spinning, but the model allowed scientists to understand times that spin was becoming so dangerous. As the sun heated the irregular lumpy surface of the nucleus, the outgassing jets didn't just push the comet forward or sideways, they also applied a torque. Imagine a spinning firework that isn't perfectly balanced. Some of its thrusters push it forward, others make it tumble and spin. The model showed this happening to Atlas on a grand scale. The constant uneven solar heating and the resulting jet activity were relentlessly spinning the comet up faster and faster. Each rotation was microscopically quicker than the last. Over weeks, the effect was profound. The comet was transforming into an unstable, wobbling gyroscope, and with this increasing spin came a new lethal force, centrifugal force. It was a pull directed from the center outwards, a relentless effort by every single particle in the nucleus to fly away. This was the ultimate betrayal. The comet's own mass, its own substance, was now actively trying to tear it apart. The model placed these three forces into a terrifying synergy. The sun's tidal forces were stretching the comet, weakening its internal structure. At the same time, the comet's accelerating spin was creating a centrifugal force that was pulling that weakened structure apart from the inside. It was being attacked from all directions at once. Gravity was pulling it, heat was vaporizing it, and its own spin was trying to fling it to pieces. The virtual comet in the supercomputer was now a perfect mirror of the real one, a cosmic pressure cooker spinning itself into a frenzy, its internal fractures spreading like cracks in a windscreen. The stage was set. The physics were in place. All that was left was to run the simulation forward and watch the final violent act. And so the team gathered. In hushed rooms across the globe, they watched the final moments of their digital ghost. On the screen, the virtual 3i, Atlas, a culmination of all this data and theory, made its final approach towards the Sunday. The numbers scrolling in the margins were almost frantic, displaying the rising thermal load, the escalating rotational velocity, the unbearable tidal shear stress. The non-gravitational jets, once almost gentle plumes, were now raging geysers blasting material into space and torquing the nucleus with incredible force. The spin rate climbed past a critical threshold, the point at which the outward centrifugal force began to overwhelm the inward pull of the comet's own pathetic gravity. The internal fault lines stressed to their absolute limit linked up, and then it happened, not as a single clean explosion but as a majestic silent structural failure. A great fissure raced across the nucleus in the simulation. A huge fragment, a mountain of ice and rock, sheared away from the main body, pushed outwards by the spin. Then another, and another. The fragile coalition of rubble that had travelled together for millennia was dissolved in a matter of hours. This was it. This was the moment the model had been built to explain. This was the gravity break. The name itself was a revelation, a redefinition of our cosmic language. It was not a break times from time's gravity, as if the comet had somehow escaped its pull. That was impossible. It was the moment gravity in its most intimate and brutal form times broke the comet asterisk. It was the precise catastrophic instant where the sun's tidal gravity, acting as a celestial anvil, met the hammer of the comet's own rotational and thermal forces. Gravity didn't let the comet go. It was the primary weapon of its execution, the force that stretched it on the rack until its own internal energies could deliver the final shattering blow. The gravity break was the culmination of the trinity of forces, a perfect storm where external stress and internal weakness converged. And in its aftermath, the model showed something even more profound. The fragments did not drift apart passively like shrapnel from an explosion. Each piece, now a tiny comet in its own right, began to fire its own jets, develop its own coma, and embark on its own unique non-gravitational trajectory. One piece, tumbling rapidly, was pushed sharply north. Another, with a large active vent, veered off on a wider, faster course. Suddenly, the bizarre, scattered paths of the real fragments made perfect sense. They weren't following a simple script. They were improvising, each one dancing to the rhythm of its own self-destruction. The model had succeeded. It had solved the impossible trajectory of 3i, Atlas. But in doing so, it had achieved something far more important. It had given us a new lens through which to view these primordial visitors. We were no longer just watching inert rocks fall through space. We were now witnessing the complex life and violent death of dynamic, evolving worlds. The ghost in the machine had not only confessed its own secrets, it had illuminated the hidden nature of every other comet drifting in the silent, patient darkness of the outer solar system, waiting for its own fiery encounter with the Sunday. The proposed model was not merely a new calculation. It was an accusation hurled at the very heart of celestial mechanics. It suggested that for decades, for centuries, we had fundamentally misunderstood the final violent act of a comet's life. The sun, long cast in the simple role of a gravitational anchor and a thermal destroyer, was now reimagined as a far more cunning and complex partner in this cosmic dance. The gravity break, as the team had named it, was more than a novel trajectory. It was a paradigm shift whispered into existence by the ghost of a dying comet, a whisper that threatened to become a roar, tearing down long-established certainties about how these icy travelers meet their end. The immediate consequence was a profound and unsettling silence in the astronomical community, the kind of quiet that precedes a storm. For if this model held true, it meant that a comet in its death throes could actively leverage the star that was destroying it to scatter its own remains with unforeseen and violent energy. The implications spiraled outwards, touching every facet of cometary science. Our carefully constructed threat assessment models for near-Earth objects were suddenly thrown into question. Those models were built upon a foundation of predictable fragmentation, where the debris of a disintegrating comet would spread out along its original path like a string of pearls, their orbits decaying in an orderly, understandable fashion. But the gravity break painted a drastically different picture. It depicted a celestial shotgun blast with fragments propelled onto new accelerated trajectories, some even potentially being kicked into different orbital planes altogether. A piece of a comet that was projected to miss Earth by millions of miles could, under this new dynamic, become a wildcard, its path dangerously altered. The comforting mathematics of Keplerian orbits, which had guided us since the 17th century, suddenly felt inadequate, almost dangerously naive. We were forced to confront the possibility that the graveyard of a comet was not a peaceful passive field of debris, but an active and chaotic system, a gravitational minefield laid by the comet itself in its final moments. This re-evaluation extended deep into the past, forcing a new look at cosmic history. For generations we have studied meteor showers, those beautiful fleeting streaks of light that grace our night sky. We understood them as Earth passing through the dusty tail, the ancient breadcrumb trail left behind by a comet on its countless journeys around the Sunday. The physics were elegant and straightforward, yet the gravity break model suggested a new source of this material, a far more violent and concentrated delivery mechanism. Could some of the more intense or unusual meteor showers in history, those that seem to appear from nowhere and defy easy association with a known parent body, actually be the result of a gravity break event that occurred centuries or even millennia ago? Perhaps what we were witnessing was not the gentle shedding of dust from a comet's tail, but the distant echoing shrapnel from a cataclysmic gravitational explosion, its debris only now intersecting Earth's orbit. The model forced us to ask a difficult question. Were we merely sailing through a comet's wake, or were we periodically crossing a forgotten interplanetary battlefield? Naturally, such a heretical idea was not met with open arms. The initial reaction from the wider scientific community was a potent mixture of intrigue and deep, unwavering skepticism. It began not in loud public pronouncements, but in the quiet, rapid-fire exchanges on academic preprint servers and the encrypted channels of university email lists. The critiques were sharp, precise, and rooted in a healthy respect for the principle of Occam's razor, that the simplest explanation is often the correct one. The established theory of cometary fragmentation was beautiful in its simplicity. Thermal stress from the sun's heat would fracture the nucleus. The pressure of sublimating gas, a phenomenon known as jetting, would create small, unpredictable thrusts. These forces, combined with the sun's immense gravity, were considered more than sufficient to explain the behavior of a comet like 3I, Atlas. Why? The critics asked. Was there a need to invent such a complex, almost baroque gravitational mechanism? The debate crystallized around this central point. Was the gravity break a genuine discovery, or was it a mathematical phantom, an overly complex solution to a problem that could be solved with existing physics? Leading dynamicists, scientists who had spent their entire careers modeling the intricate ballets of the solar system, argued that the team behind the new model had failed to properly account for the chaotic effects of jetting from the numerous fragments. A comet's nucleus is not a uniform block of ice. It is a heterogeneous mixture of ices, dust and rock, a dirty snowball riddled with fissures and pockets of volatile compounds. As a fragment tumbles through space, new surfaces are exposed to the sun's glare, creating unpredictable jets of gas that act like tiny sputtering rocket engines. The critics postulated that a carefully synchronized, albeit coincidental series of these jetting events from the largest fragments could produce the exact same observational signature as the so-called gravity break. They argued it was a case of seeing a complex pattern where none existed, of mistaking the random noise of cometary disintegration for a new symphony of gravitational whispers. The skepticism was not malicious. It was the essential grinding process of scientific validation at work. Every revolutionary idea must pass through the crucible of doubt. The burden of proof lay squarely on the shoulders of the model's creators. Their elegant equations and compelling simulations were not enough. They needed more than a theory that fit the existing sparse data. They needed a theory that could make new, specific, and falsifiable predictions. They had to prove that what they were seeing was not the result of 1,000 random pushes from gas jets, but the unmistakable unified signature of a gravitational convulsion. The fate of their model rested not in the supercomputers where it was born, but in the cold, hard light being gathered by telescopes around the world, light from the very fragments that were at the center of the dispute. The shattered remains of 3I, Atlas, were no longer just pieces of a comet. They had become the jury that would deliver a verdict on this audacious new chapter in our understanding of the cosmos. And so began the painstaking, grueling work of vindication. The challenge was immense, akin to trying to reconstruct the precise mechanics of a mid-air explosion by tracking the trajectory of every single piece of shrapnel. The team knew their model's predictions were wildly different from those of the standard jetting hypothesis. While a jetting-based fragmentation would result in a somewhat random, diffuse scattering of debris, their gravity brake model predicted something far more specific and bizarrely organized. It foretold a clear hierarchy of motion. The fragments flung forward along the comet's original path, those caught in the gravitational tailwind of the brake, should exhibit a slight but measurable acceleration, moving faster than gravity alone could account for. Conversely, the pieces scattered backwards, those on the opposing side of the event, should be decelerating, appearing to lag behind their expected positions as if caught in a gravitational headwind. Most critically, the model predicted subtle but distinct changes in the orbital inclination of the outermost fragments, a twisting motion that simple jetting could not easily replicate on a consistent, coordinated scale across multiple pieces. This was their battleground. Over the ensuing weeks, a global network of observatories was commandeered in a silent, coordinated effort. From the towering peaks of Mauna Kea to the arid deserts of Chile, powerful telescopes focused their gaze on the ghostly cloud of debris where 3I, Atlas, used to be. The work was tedious and repetitive, demanding immense precision. Night after night, astronomers would capture hundreds of images, their sensors meticulously charting the faint points of light against a backdrop of distant stars. Each image was a snapshot in time, a single frame in the grand unfolding story of the comet's demise. These raw images were then relayed to the modeling team, where a frantic, round-the-clock effort was underway to process the deluge of information. The first step was always the most difficult, identifying and labeling each individual fragment amidst the noise of the glowing coma. It was like trying to track a handful of specific snowflakes in the heart of a blizzard. Once a fragment was confidently identified across multiple nights of observation, its position could be calculated with astonishing accuracy. The team's software then went to work plotting the nascent orbit of each piece of cosmic wreckage. For every single fragment, they would run 2 simulations. The first was the null hypothesis, the classical model. It incorporated the sun's gravity, the gravitational pull of the planets, the gentle but persistent push of solar radiation pressure, and even a generous randomized jetting factor representing the arguments of their critics. The second simulation was their own, the gravity brake model. The 2 simulations would start from the same point with the same initial data, but they would predict subtly different futures for each piece of debris. The question was simple: which future would the real fragments of Atlas choose to follow? The first results were tantalizing but inconclusive. For the larger, brighter fragments near the center of the debris cloud, both models performed reasonably well. The differences in their predicted paths were so small that they were lost within the margin of error of the observations. The skeptics felt a quiet sense of justification. The simpler explanation, it seemed, was holding its ground. But the model's proponents urged patience. Their theory predicted the most dramatic effects would be seen not in the core but on the fringes of the debris field, in the smaller, fainter fragments that had been flung the furthest. These were the most difficult targets, their faint light barely registering on even the most sensitive detectors. It was a hunt for ghosts on the edge of visibility. Then came the breakthrough. A team using the Subaru telescope in Hawaii managed to secure a deep, long-exposure observation of the outermost edge of the debris cloud. Buried in the digital noise of the image were three faint, previously uncatalogued fragments designated C14, C15, and C16. They were small, perhaps no larger than a school bus, and they were far from the main cluster. When their positions were fed into the system, a wave of excitement washed over the modelling team. The standard model, even with the most aggressive jetting parameters imaginable, failed spectacularly. It predicted the fragments should be several 100,000 kilometers away from their observed positions. It simply could not account for their tremendous velocity and their slightly skewed orbital plane. They were moving too fast and flying too high. Then they ran their own simulation. The room fell silent as the numbers appeared on the screen. The gravity brake model didn't just come close, it was a near-perfect match. It predicted the positions of C14, C15, and C16 to within the width of the telescope's own margin for error. It was as if the comet's ghost had reached out across the solar system and pointed precisely to where its lost children would be found. The model had correctly predicted the bizarre acceleration of these outlying pieces, an acceleration that defied conventional explanation. It had correctly predicted their subtle but undeniable twist in inclination. The random sputtering of gas jets could not have achieved such a coordinated, powerful effect across three separate fragments. This was the signature they had been looking for. This was not noise. It was the clear, resonant echo of a powerful, unified gravitational event. One by one, as more data from other faint fragments trickled in, the same pattern emerged. A fragment designated B9, which was on a trailing trajectory, was observed to be moving slower than any classical model could justify its motion, arrested as if by an invisible brake, just as their model had foretold for the debris, flung backwards from the event. Each new data point was another nail in the coffin of the old paradigm. The painstaking process of observation, modeling, and comparison was transforming a controversial hypothesis into a robust, evidence-backed theory. The skepticism in the broader community began to soften, replaced by a growing sense of awe and excitement. The initial accusations of needless complexity were fading, replaced by the admission that the universe is perhaps more complex and wonderful than our simple models had previously allowed. The team had done more than just track a dying comet. They had pioneered a new forensic science for the cosmos, learning how to read the spatter pattern of a celestial disintegration to understand the weapon that was used. The shattered pieces of 3I, Atlas, were no longer just a cloud of debris. They had become a meticulously preserved crime scene, and the gravity brake model was the key to deciphering the extraordinary story written in its wreckage. The model was now more than just a theory. It was a newly validated tool, a new lens through which we could view the solar system. The immediate debate was settling, but the real work was just beginning. If a gravity brake could happen to an interstellar visitor like Atlas, could it happen to others? Could this powerful unseen mechanism be a common, yet previously unnoticed feature in the life of comets throughout our solar system and beyond? The answers to those questions promised to reshape our understanding of how our own planetary neighborhood was built and how the seeds of life itself may have been delivered across the vastness of interstellar space. The calculations were complete, the digital ghosts of Atlas's future plotted across 1,000 simulations, but a model, no matter how elegant, remains a hypothesis, a fragile promise waiting for the universe to either honor or shatter it. For the team behind the new trajectory model, the weeks that followed its daring publication were an agonizing vigil, a period where every photon captured by telescopes worldwide could be either absolute vindication or utter refutation. They had thrown down a gauntlet not of arrogance, but of profound belief in their new mathematics. They had claimed to understand the phantom forces guiding the comet's children, to have foreseen the intricate choreography of its disintegration. Now all they could do was wait and watch the heavens. The universe in its own time would deliver its verdict. The first test came from the largest, brightest remnant, the vanguard of the ghostly procession designated Atlas A. Our previous models, the ones that had failed so spectacularly before the breakup, had struggled with this fragment from the very beginning. They saw its path deviating, pushed by an invisible hand. This was the classic signature of outgassing of jets of vapor acting like miniature thrusters. But the new trajectory model had made a far more specific, more perilous prediction. It proposed that fragment A, having been the most exposed part of the original nucleus, was already depleting its most volatile surface ices. Consequently, its non-gravitational acceleration, that mysterious push, should not be constant. It should be decaying, weakening day by day along a very precise curve as its fuel was steadily spent. This was a forecast of exquisite detail, a prediction not just of movement, but of a change in the nature times of that movement. For weeks, the data that trickled in from mountaintop observatories was ambiguous, lost in the noise of atmospheric distortion and the sheer faintness of the object. Then the Hubble Space Telescope was given its window. Floating in the silent vacuum above the blurring effects of Earth's air, its vision was pristine. Over a period of 72 hours, it locked onto the faint smudge of fragment A, measuring its position against the backdrop of distant stars with breathtaking precision. The team watched as the data points populated their graphs, their hearts pounding in a shared rhythm of anticipation and dread. At first, the points seemed to align with the older, simpler models, but as more data accrued, a subtle, unmistakable trend began to emerge. The fragment was not accelerating as much as it had the day before. The push was fading. When they overlaid the NTM's predicted decay curve onto the Hubble data, the alignment was spine-chilling. The points didn't just cluster around the line, they fell directly upon it, a near-perfect match. It was as if the universe had traced their mathematics across the void. The model hadn't just been right, it had been prophetic. The invisible hand pushing Atlas A was slowly, predictably weakening its grip exactly as the new physics had foretold. This was the first piece of the puzzle to click into place, a resounding affirmation that they were on the right path. But the case for the NTM was far from closed. The true test of its power lay not with the largest, most predictable fragment, but with the chaotic behavior of its smaller, more erratically behaved siblings. The model's simulations had suggested something truly strange about the second brightest piece, Atlas B. As it carved from the parent body, the simulations argued the uneven force of the escaping gases would have imparted a violent spin, sending it into a chaotic tumble. This wasn't a smooth planetary rotation. This was a wobble, an unpredictable gyration through space. Such a motion would be impossible to observe directly, but the model made another, more accessible prediction. This chaotic tumbling would expose different icy patches to the sun in a disorderly pattern, causing its brightness to flicker and pulse, not with a regular period, but with a complex, almost random-seeming light curve. It was a forecast of beautiful, predictable chaos. To test it, astronomers turned to photometry, the science of measuring the subtle changes in the intensity of light from celestial objects. Night after night, they monitored fragment B, a tiny pinprick of light dancing at the very edge of visibility. The early data was a mess, a noisy, jagged line that seemed to signify nothing, but as they integrated hundreds of observations, filtering out the instrumental noise and the atmospheric shimmer, a pattern began to resolve itself from the static. It was not the clean, repeating sine wave of a stable, rotating body. Instead, it was a complex tapestry of peaks and troughs, of sudden flares and deep fades, a signature of profound instability. The team fed this observed light curve into their computers, asking for a comparison against the thousands of simulated light curves generated by the NTM. The search algorithm churned for hours, sifting through a sea of possibilities. And then it found a match. One specific simulation, which modeled fragment B as a shard of specific dimensions tumbling with a particular chaotic wobble, produced a light curve that was a statistical mirror of the one observed in the sky. The flickers, the flares, the fades, they all aligned. You could feel the collective exhale travel across continents as the team members shared the news. They hadn't just predicted a path, they had predicted a dance, the wild, untamed pirouette of a dying shard of ice millions of miles away. The validation grew stronger still with the curious case of fragments C and D. These two pieces were smaller, fainter, and born later in the disintegration sequence. What made them special was their proximity. The NTM projected that for a few precious weeks following their creation, they would be close enough to feel each other's minuscule gravitational pull. They would orbit one another in a delicate, fleeting embrace, a temporary binary system of cometary debris. It was a whisper of gravity in a system dominated by the sun's shout and the push of outgassing. The prediction was that their separation would increase not linearly, but in a staggered, oscillating way as they gently tugged and pulled on one another while drifting apart. This was the model's most audacious claim yet, an attempt to measure the gravitational heartbeat between two pieces of cosmic dust. Capturing evidence for this would require imagery of almost unbelievable resolution, pushing the world's best telescopes to their absolute limits. The challenge was accepted by the European Southern Observatory's Very Large Telescope in Chile, which used a technique called adaptive optics to cancel out atmospheric turbulence in real time. The resulting images were masterpieces of clarity. In them, fragments C and D were not a single blur but two distinct points of light, their separation measurable down to the milliarcsecond. Over a month of painstaking observation, astronomers tracked their relative positions, plotting their separation day by day. The result was astonishing. The distance between them did not grow smoothly. It expanded, then slowed, then expanded again, a subtle gravitational waltz playing out exactly as the NTM had choreographed. The two fragments were indeed dancing to gravity's tune, their feeble attraction to one another acting as a gentle brake on their departure. It was the ultimate proof of the model's sophistication. It could account not only for the overwhelming power of the sun and the propulsive force of sublimating ice, but also for the almost imperceptible gravitational whisper between the comet's own children. The model was seeing the entire system, a complete ecosystem of forces in delicate dynamic balance. With the major fragments now accounted for their trajectories validated with stunning accuracy, the team could turn to the final, most ethereal piece of the puzzle, the vast, ghostly veil of dust that enveloped the entire procession. The NTM wasn't just a tool for tracking solid bodies. Its physics engine also simulated the release of millions of individual dust grains, each one blasted from the nucleus, and then guided by the gentle but relentless pressure of sunlight. The model predicted that these microscopic particles, sorted by size and ejection velocity, would form a distinct fan-shaped tail with a specific curvature and density profile. This was the comet's memory, the lingering ghost of its former self, and the model claimed to know its precise shape. Verifying this required a different kind of eye, one sensitive not to visible light, but to the faint thermal glow of sun-warmed dust. The now-retired Spitzer Space Telescope, in one of its final observation campaigns, was perfectly suited for this task. Its infrared vision pierced through the glare, revealing the delicate architecture of the dust trail. When the Spitzer image was processed and laid over the NTM's dust simulation, the two were indistinguishable. The predicted filaments, the subtle clumping of material, the graceful curve of the tail as it was swept back by solar radiation, every feature was present. The model had not only predicted the fate of the shards, but it had also perfectly rendered the form of their collective ghost. Every major prediction had been met with resounding confirmation. Every piece of the puzzle, from the lumbering giant of fragment A to the tumbling dance of B and the gravitational embrace of C and D, had clicked perfectly into the framework the NTM had built. The model worked. It worked with a fidelity that bordered on the magical. And, with this newfound unshakable confidence, the team could finally perform the ultimate feat. They could run the simulation in reverse. They could take the known verified positions and velocities of every fragment and trace their journeys backward in time, back to the moment of their violent birth. This was the key that would finally unlock the mystery of the gravity break itself. As they watched the simulation rewind, the fragments flying back towards their origin point, the true nature of the event was revealed, and it was more complex and more elegant than anyone had dared to imagine. The gravity break was not a single instantaneous explosion, a catastrophic rupture that happened in a flash. The model showed it as something far more organic, a slow, progressive failure, a story told in a cascade of fractures over several days. The initial trigger was the comet's rapid rotation, which had been spun up by outgassing jets as it neared the sunday. This spin created centrifugal forces that were already pulling the nucleus apart. As it crossed a subtle gravitational resonance line in its orbit, the added tidal stress from the sun was like the final straw. The first deep fracture appeared, shearing off the chunk that would become fragment A. This initial separation was not explosive. It was a quiet, inexorable parting. But this event catastrophically unbalanced the remaining nucleus. Now spinning unevenly, it began to wobble violently. This wobble concentrated new stresses on its already fragile structure. Hours later, a second major fracture occurred, releasing the tumbling shard of fragment B. Finally, days after the initial event, the core of the nucleus, now hopelessly compromised, crumbled into a collection of smaller pieces, including the duo of C and D. There it was. A complete cohesive narrative from start to finish. The gravity break was a sequence, a story of structural collapse, with each breakup event triggering the next in a fatal chain reaction. The model, now fully validated, provided a definitive moment-by-moment account of a comet's death throes. It explained everything. It explained why the initial observations seemed so confusing, showing a gradual fade before a sudden reappearance of multiple objects. It explained the different trajectories, spins, and accelerations of each individual piece as a direct consequence of the specific way it broke off. The once baffling mystery had been resolved into a breathtakingly complex yet entirely predictable interplay of rotation, outgassing, and gravity. A sense of profound resolution settled over the astronomical community. It was a moment of quiet intellectual triumph, the kind of victory that scientists live for. In the precise, beautiful agreement between their abstract mathematics and the stark reality of the cosmos, they had done more than simply track a disintegrating comet. They had deciphered a language spoken in gravity and light, and in doing so had translated a story of cosmic dissolution from a perplexing enigma into a testament to the predictive power of human understanding. The saga of Comet Atlas, the object that broke all the rules, was finally completely understood. And so the strange pilgrimage of 3I, Atlas, comes to its final astonishing revelation. We watched it slip into our system, a whisper from the void. We saw it defy our predictions, a celestial ghost refusing to follow the script, and now we understand why. The gravity break was not merely a unique event, it was a lesson written in disintegrating ice and dust across the vast blackboard of space. It was the universe compelling us to look closer, to think deeper, and to abandon the comforting certainties of the past. The new trajectory model, born from the ashes of our failed predictions, is far more than just a new set of equations. It represents a fundamental shift in our perception, a new lens through which we can now view the endless river of cosmic travelers. It is the key that has unlocked a door we didn't even know existed. For generations, our understanding of celestial mechanics has been built upon a magnificent, solid foundation. We imagined comets and asteroids as singular monolithic objects like cosmic cannonballs fired across the solar system, their paths governed by the elegant and predictable laws of gravity. Outgassing from a comet's nucleus, the jets of vaporizing ice was the only accepted variable, a slight chaotic push that could gently nudge these travelers from their gravitational rails. But Atlas shattered that simple, elegant picture. It showed us that some visitors from the interstellar dark are not solid cannonballs at all. Instead, they are fragile congregations, loosely bound collections of primordial rubble, ancient ice and dust, held together by forces so tenuous they barely qualify as a single object. You have to imagine not a solid ship navigating the ocean, but a raft of logs tied together with aging rope sailing into a storm. The sun's gravitational field in this new reality is not just a smooth, curving roadway. For a body as fragile as 3I, Atlas it is, a treacherous landscape of tidal forces, a gravitational torture rack that stretches and pulls on these loosely bound aggregates. The gravity break was the moment the ropes on that cosmic raft began to snap. It wasn't a singular violent explosion, but a cascade of internal failures, a structural sigh of surrender. Each piece, now liberated, began to chart its own slightly different course, creating a subtle collective drag against the comet's momentum. This was the braking force, the mysterious hand that slowed Atlas down, a phenomenon our old models were utterly blind to. The new trajectory model accounts for this internal fragility, for this structural complexity. It allows us to simulate not just a single point of light, but a distributed crumbling mass, and to predict how it will behave under immense gravitational stress. This isn't just an upgrade, it's a revolution in computational astrophysics. We have moved from treating these objects as simple billiard balls to understanding them as complex evolving systems with their own internal geology, their own histories, and their own breaking points. This revelation sends profound ripples through the entire field of cometary science. These icy wanderers, long cherished as pristine time capsules from the birth of our solar system, are now revealed to be even more delicate, more ephemeral than we ever imagined. Think of what this means for their life cycles. We now understand that many comets may not survive even their first fiery passage around a star. They might arrive as seemingly coherent bodies, only to be gently but inexorably dismantled by tidal forces long before they can put on a spectacular show. Their death is not always a brilliant, explosive finale, but often a quiet, graceful disintegration, a slow-motion surrender to gravity. This new perspective forces us to reconsider the entire cometary population. How many comets have we misidentified? How many seemingly dim or inactive objects were once larger bodies that have already undergone a partial gravity break on a previous orbit? The model provides us with a new diagnostic tool, a way to rewind the clock on a comet's trajectory and search for the telltale signs of past fragmentation events, revealing a hidden history of near-death experiences. Furthermore, this changes how we think about the very origins of these objects. The extraordinary fragility of 3I Atlas suggests it was formed in a uniquely gentle environment, a place far from the violent gravitational churning that would have consolidated material into more robust, solid bodies. Its structure hints at a slow, delicate accretion in the frigid, undisturbed outer reaches of its parent star system, a place where icy grains could clump together like snowflakes rather than being smashed into a solid mass. When we see a comet like Atlas, we are not just seeing a relic from the dawn of another solar system, we are seeing a direct sample of its most placid, most remote, and most ancient nursery. It is a messenger, carrying not just chemical information but structural information, telling us a story about the tranquility or turbulence of its distant birthplace. Every fragile, loosely bound interstellar comet we find from now on will be another vital clue in the grand puzzle of planetary formation across our galaxy. It will allow us to become cosmic sociologists, studying the different environments in which planetary systems are born, all without ever leaving our own cosmic backyard. The impact on our search for interstellar visitors is perhaps the most immediate and exciting consequence of this new understanding. Before Atlas, the hunt for objects like Oumuamua was a search for anomalies of motion defined by pure speed and trajectory. We were looking for travelers moving too fast to be gravitationally bound to our sun objects on a clear and irreversible path of entry and exit. But the gravity break of Atlas has given us a completely new and far more subtle signature to search for. We now know that interstellar wanderers, especially those with this fragile aggregate structure, might not announce their presence with overwhelming speed. Instead, they might betray their alien origins through their behavior. We can now train our telescopes and our computer algorithms to hunt for objects that undergo minute, unexplained changes in trajectory as they approach the sun, changes that cannot be accounted for by outgassing alone. Imagine the scene in our planet's observatories and data centers. Astronomers are no longer just looking for the fastest thing in the sky. They are now celestial detectives searching for evidence of a crime scene, for the subtle braking effect that indicates a body is undergoing internal structural failure. It's a paradigm shift from searching for the sprinter to searching for the marathon runner who stumbles near the finish line. This new search criterion dramatically widens the net. We might find interstellar objects masquerading as typical solar system comets, their true nature only revealed by the sophisticated analysis of the new trajectory model. We might discover that our solar system has been visited far more frequently than we ever dared to believe, but that many of these visitors were simply too subtle, too well behaved for our old methods to flag. 3I Atlas wasn't just a visitor, it was a teacher giving us a new language to listen for in the cosmic darkness, a new way to identify the quietest guests at our solar system's door. The next interstellar object we find might not be announced by a flashing headline about its incredible speed, but by a quiet scientific paper detailing its inexplicable deceleration, a whisper that only the new trajectory model can translate. This entire saga has also been a powerful catalyst for our observational capabilities. The perplexing behavior of 3I Atlas created a desperate need for more data more frequently and from every conceivable angle. It forced an unprecedented level of global collaboration. Telescopes across the planet, both professional and amateur, coordinated their observations in a way rarely seen before. Space-based observatories like Hubble were retasked with urgency to capture the disintegration in exquisite detail. This event stress-tested our entire planetary defense and rapid response observation network. We learned what worked, and more importantly, what didn't. In the wake of Atlas, new protocols have been developed, new software written to allow for a more agile and integrated response to a perplexing new object. We are better prepared now to swing the world's observational might onto a single fleeting target to gather the crucial data needed before a visitor like Atlas fades back into the darkness. Moreover, it pushed the boundaries of what we thought was possible with data analysis. The need to understand the comet's breakup spurred the development of new image processing techniques to track the motion of individual fragments within the expanding dust cloud. It inspired new spectroscopic methods to analyze the chemical composition of the material being released, not just from the nucleus as a whole, but from different fragmenting regions. We were forced to innovate on the fly, developing tools in months that might normally have taken years of theoretical work. This technological leap forward is one of the most enduring legacies of 3I, Atlas. We now have a more powerful, more responsive, and more sophisticated toolkit at our disposal, ready for the next cosmic surprise that comes our way. Whether it's another interstellar traveler, a potentially hazardous asteroid, or a peculiar comet from our own Oort cloud, the lessons learned from the Atlas campaign have made us sharper, faster, and more capable observers of the celestial drama. So where does this leave us? We stand at the end of this remarkable journey, looking back at the faint, ghostly trail of a comet that no longer exists in its original form. 3I, Atlas, has dissolved its constituent parts now on their own. Lonely orbits, a scattered memory of the object that once was. But what it built in its place is something far more permanent. It built a new foundation for our understanding of the universe. It taught us that the cosmos is not always governed by brute force and simple sweeping laws. It is a place of immense subtlety, of profound fragility, a realm where the delicate internal structure of a tiny body can defy the immense gravitational power of a star. It reminds us that our solar system is not an isolated fortress, but a dynamic open ecosystem constantly visited by messengers from other stellar shores. Each visitor carries a story, a piece of a galactic puzzle we are only just beginning to assemble. The new trajectory model, the legacy of Atlas, is now a permanent part of our astronomical arsenal. It prepares us not just for scientific discovery, but for our own future as a spacefaring species. Understanding the structural integrity of comets and asteroids is no longer a purely academic exercise. It is essential for planetary defense, for predicting how a potential impactor might behave upon entering our atmosphere. It is crucial for future resource utilization, for knowing whether an asteroid we hope to mine is a solid rock or a treacherous pile of rubble. And it is vital for our ongoing quest to understand our own origins, as we refine our models of how the early solar system was seeded with the water and organic materials that comets carry. Atlas, in its quiet act of self-destruction, has made us safer, smarter, and more capable explorers. Ultimately, the story of 3I, Atlas, is a profound lesson in cosmic humility. It is a reminder that just when we think we have the universe figured out, just when our models seem perfect and our predictions certain, a faint smudge of light will appear in the darkness to show us how much we still have to learn. It reveals a universe that is not a static clockwork mechanism, but a place of constant creation, destruction, and surprising transformation. The dance of celestial bodies is more intricate, more complex, and more beautiful than we ever gave it credit for. And we, on this small blue world, are privileged to have a front row seat. We are the witnesses, the interpreters, the storytellers. And thanks to a fragile visitor from an unknown star, our ability to read the story written in the stars has been changed forever. The next time you look up into the night sky, remember Atlas. Remember that the silence is filled with unseen travelers, each on its own epic journey. And remember that the most profound secrets of the cosmos are often revealed not in the fury of a supernova, but in the quiet, graceful surrender of a distant, lonely comet.